If a particle, we shall discuss the de-Broglie hypothesis tomorrow, but I'll give some input for that one, okay? Now, suppose if radiation have got particle nature, okay? If radiation have got particle nature, or if light have got particle nature, light was believed to be a wave, isn't it? Because it undergoes interference and so diffraction. It has a you have Maxwell electromagnetic theory, very strong, isn't it? If it has a dual nature, if it has particle behavior, okay, why can't particle can have wave behavior? It looks silly, but I think in 1928 only, isn't it? De-Broglie proposed the hypothesis, de-Broglie hypothesis. He said all material particle, okay, suppose there is a particle which is moving with a momentum p. I'll say momentum p because momentum is the most general term. If you write p equal to mv, that is non-relativistic equation, okay? So in case of relativity, also the similar equation holds, okay? If there is a particle which moves with a momentum p, so again it has a wave nature associated with it. It has a wave behavior associated with it. Once you say it has a wave behavior, then it should undergo interference and diffraction. Once it undergoes interference and diffraction, those experiments are sensitive to wavelength, isn't it? Those experimental outcomes are sensitive to wavelength. The question comes, if it has a wave behavior, what is the wavelength of that wave, whatever we are talking about? He called that one as matter wave. Okay, so that wavelength is equal to h by momentum of the particle. I'm talking about matter. In case of non-relativistic case, you can write h by m into v. Is that okay? And later it is verified, isn't it? This happens in the history of physics. Hypothesis, some ideas, then later it is verified, isn't it? I think after 4 years, again it is verified by Davison and Germer. Let me explain that Davison and Germer experiment tomorrow. So now it looks like very silly argument. Look at here. This is, I think, as I heard, this is 1 or 2 page derivation. Okay, lambda is again it's a combination of E equal to mc square is equal to h nu. So he clubbed those two equations and he just derived that one. So later thousands of books were written on that one actually. Now look at here. Now once I say that all particles have got wave nature, okay, look at here how I am going to proceed. I said all particles have got wave nature lambda is equal to h by p, isn't it? Now I'll go back and I'll say light composed of photon has wave nature. And wavelength associated with a photon is equal to h by p. What is p? C by nu. That is true, isn't it? This relation is true, isn't it? Photon also follows the same. Again, what is the de-Broglie wavelength of photon? That is wavelength of radiation itself. Why not? Are you getting my idea? Once I say all material particles have wave behavior, and I'll go back and I say light composed of photon, light composed of particle only, that particle have got wave behavior. You should generate some question here.
Is this the wave behavior that Dirac talks about as the form of linear probabilities and translation probabilities?
Wait.
Reflection and interference.
Why probability comes? I didn't introduce.
So sir, interference, reflection,
No, I didn't talk about probability. Why probability comes?
You were saying about wavelengths, right? Amplitudes and wavelengths. So that's what I'm asking. Is this the same wavelength of what Dirac talks about as linear amplitudes of different stream of particles of photons during interference? What he says as these are. Is that the same wavelength behavior? Is that the same wave behavior?
No, wait a second. I didn't get that one. Again, linear wavelength. No, yeah, wait a second. I'll close my idea. Look at here. We said it is matter wave, am I right? We haven't said what kind of wave it is. What kind of wave again, look at here. This is also called as de-Broglie wave. Look at here. Look at their inability. So if somebody, if suppose he's going to, if you are proposing some new thing, new wave, and you yourself don't know what it is, then what will I say? That is Gentoo's wave, isn't it? Isn't it? So that is Gentoo's wave. Like that, look at here. They said that one is de-Broglie wave. We don't know what kind of wave it is. So that's why it's like incomplete. I mean, it's not a framework. It's also incomplete. Okay, but it is true. But it is true. But we need to find why this happens. Okay, we need to find why this wave behavior happens. So that's why we go for, again, if it has a wave behavior, then it should follow interference and diffraction, isn't it? So that is the deviation-German experiment, so diffraction experiment, isn't it? So now what we do is we go to those experiments. Again, we try to explain that experiment in a new fashion. That is again my next topic, that is double slit experiment. Is that okay? Wait a second. So tomorrow I'll explain this one again and then I'll proceed, okay? I need much more words here, yeah.
Matter waves play very crucial role in.
Yeah, in the history. In the history it plays very crucial role.
Please repeat the de-Broglie wave. What you have said actually my internet connection has been lost.
No, again, look at here. All material particle which is moving with some velocity, which has some momentum v. So look at here, the word, it associated with the wave behavior, okay? It have got wave behavior. If it has a wave behavior, you should define wavelength, isn't it? Because interference and diffraction needs wavelength to be defined. Later in quantum mechanics, nowhere you define wavelength. You know that one? Where you define wavelength of particle?
No.
Nowhere, later. So that's what I'm saying. Again, so later they will deviate and they will give some different approach to this one. So again, a particle has a wave behavior. Once you say it has a wave behavior, then to explain interference and diffraction, you need wavelength of that, whatever wave you are talking about. That wavelength is equal to h by p. That wave is called as matter wave or de-Broglie wave. That is, we don't know. That is not electromagnetic wave. That's not sound wave. That's not water wave. We don't know what kind of wave it is. What kind of wave de-Broglie wave is?
Then the solution of the de-Broglie wavelength is nothing.
No. De-Broglie wavelength is there. This is used for those experiments. You will find maxima, minima and pattern, isn't it? More number of particles received at one position, less number of particles received at other position, isn't it? Fringe width, whatever you get, isn't it? Those should be related to some wavelength, am I right? Okay, look at here. Our perception of that interference and diffraction wave theory, so that leads to what you call, if there is wave behavior, there should be wavelength. That's our perception, isn't it? If there is wave behavior, there should be wavelength. Now later we are going to give different approach for this one. Wave behavior is because of some nature. Nature is playing a kind of probability stuff actually. Because of that, this wave behavior comes. And we are going to understand that probability stuff. That is a new theory, that's the quantum mechanics.
When particle is behaving like a wave nature and when it is like a particle nature. When it shows a particle nature and when it shows
Again, we said dual nature, am I right? We said dual nature. I think you better take time and watch those videos whenever you get time, okay? Class 12th videos. Again, this dual nature of light, okay? Dual nature of light. Again, when you perform the experiment of interference diffraction, it manifests wave behavior. We say like that, okay? We say like that. Now I'm going to edit that one, edit those statements, okay? Because we have new theory here, okay? For that new theory, I'm going to edit those statements. So because those are our old perceptions actually, okay? So now, if you perform another experiment like Compton effect or photoelectric effect, it will show a spark particle behavior. Are you getting my point? Depending on the experiment you do on that stuff, it will show off its behavior. If you take any collision event or something, electron can be collide with something, isn't it? Or it can do some reflection or something here, isn't it? So again, so it may show particle behavior. Are you getting my point? Suppose if you do some Davidson-Germer experiment, G.P. Thomson experiment, kind of diffraction or interference experiment, it will show wave behavior.
Sir, may I speak some?
Yes, yes.
Sir, here the Dirac says translational states are thus superposable in similar wave to wave functions. The wavelength that you were talking about for the photon, is that the wavelength of the wave functions of the photon?
No. Yeah, again, if you say for a free particle with a definite momentum, this is the wavelength of whatever the, again, wave function is not any amplitude of any electric field or magnetic field or something, okay? I'll try to correct this one.
I know, it's a probabilistic wave.
Got it. You are saying we write e power I kx, okay? Free particle Schrodinger equation solution. We write like that.
For photon, you said the wavelength was c by nu. Is that the wavelength of this wave function, this probabilistic wave function? For a photon, you said that, right? That a photon must have a wave behavior. So
yeah, so this wavelength is exactly the same wavelength that you are talking about. If you write your wave function like this, k again, so h bar k is a momentum, isn't it?
yeah.
H bar k is nothing but 2 pi by lambda, okay? H by 2 pi, p is equal to h by lambda. That's exactly correct. But wait a second, again, that superposable, whatever you said, those are extra terms that you introduced now. Please wait for a while. You know some quantum mechanics already, isn't it? Wait for a while, because again, for a free particle with definite momentum, this kind of state doesn't exist in quantum mechanics. Look at here, definite momentum state. Uncertainty will be violated. Again, we are just before quantum mechanics, okay? Don't think of quantum mechanics now. Now, what I am saying is, whatever the wave function you talk about, look at here, that word itself is misleading, okay? It talks only about probability. It will not give any other interpretation of real wave actually. Are you getting my point? That's what we need to learn here, okay? I'll try to propose this one. I'll come to this point, okay? I'll come to this point. Yeah. So now look at here. So what I'm thinking here is, yeah. Now later what I do is, everything is particle, okay? Light is also particle, electron is also particle. But no, again, we are macroscopic, I'm talking microscopic, be careful, okay? So that's also particle, this is also particle. But wave behavior might have happened because of some natural mechanism. And we need to learn that mechanism. Our double slit experiment will help us to learn that one. Nature is doing some more, things. We need to find out that one. Then we take some experiment and we are going to closely observe that one, trying to interpret, and we are going to learn what is the gimmick that nature is doing, like that. Then we will try to do the framework of the theory. Are you getting my point? So definitely this de-Broglie hypothesis, so it led to the theory, no doubt. So when this is proposed, 1923, isn't it? Yeah. I think I better to stop this one, because I need to take some basic math interview. Should not compromise with our interview sessions. How to find de-Broglie wavelength of electron in the ground state of harmonic oscillator. Bound particle, isn't it? Now look at here, de-Broglie wavelength is well defined only for definite momentum state, okay? No. A harmonic oscillator, you have uncertainty in momentum. A particle in box, harmonic oscillator. Hold for a while, okay? If you have this kind of question, which is from quantum mechanics, okay? You write down that one, okay? Linear combination of de-Broglie waves. You can say like that. Again, it contains many momentum state, where that we call that one as uncertainty. So anyway, we shall talk about that one in the further session, okay? So de-Broglie hypothesis, am I right? So what do you mean by hypothesis? Can anyone define? Hypothesis. Can anyone define hypothesis? Can you hear me?
Which is not experimentally proven.
Speak out.
Which is not experimentally proven.
Yeah, which is not experimentally proven. What do you mean by postulate then? So there are two things here. Am I right? Postulate and hypothesis. Which? Huh.
The hypothesis means a tentative generalization whose validity is to be tested.
Hypothesis. Yeah. Again, what about postulate? Postulate is something which is built for explaining something. Am I right? Which is already there in the experiment. Am I right?
Yes. Yes, sir.
Huh.
The hypothesis
Yeah.
is to be tested further.
Yes. Now look at here again. It says all material particle have got wave behavior, wave property, and the wave what you call that wave of that material particle, we call it as matter wave. Am I right? Matter wave. Or de-Broglie, again look at here. Light we say electromagnetic wave, isn't it? Suppose if you talk about wave on a water surface, we call that one as mechanical wave. Now since it is a wave wave which is related to matter, we say matter wave. So wave related to suppose Subramanya. I suppose if I define some new thing, okay, so then it is his wave, like that we say. So similarly de-Broglie wave, because we don't know what it is. So it's called as matter wave or de-Broglie wave. Again, once you say it is a wave, it has a wave nature, okay. So then one thing that you need to keep in mind is again, if it has a wave nature, then it should follow interference and diffraction. If it follows interference and diffraction, then definitely it should you should define wavelength. Am I right? Because our optics and other interference and diffraction experiment, those are very sensitive to wavelength of the incident radiation. So that's why you need to define wavelength of that one. So lambda is equal to h by p. If suppose material particle which is moving with momentum p, so then wavelength associated with its matter wave is called as de-Broglie wavelength. We call this one as de-Broglie wavelength. That's equal to h by p. P can be written as m into v in case of non-relativistic domain. Okay. Yes. Now look at here. Yeah, he proposed that one. So all material particles have wave behavior. I think in 1928. Later you need to again. So in 1932 it is proved in lab, isn't it? Now look at here. That experiment is like this. So what is X-ray? What is X-ray? It's an electromagnetic radiation, isn't it? X-ray undergoes interference and diffraction, isn't it? So now again we are going to use this X-ray to study crystal structure. I hope you know, isn't it? So to study crystal structure, we are going to use X-ray diffraction, isn't it? So now I'm going to take what you call crystal. Okay. So again, so crystal means regular arrangement of atoms. Am I right? It contains regular arrangement of atom. I'm going to take regular arrangement of atoms here.
I think they are using nickel.
Yeah, nickel crystal. But let me quickly discuss that Bragg law. So then again, I hope you all know that one. I'll briefly discuss that one. Okay. Suppose X-ray incident on first plane. Okay. So this is first plane of the crystal. This is second plane of the crystal. Like that, you can so design other plane. Okay. We shall discuss these things in crystallography. Yeah. So now look at here. In case of that X-ray diffraction, okay, we say XRD. In case of that X-ray diffraction, so again wave reflected from first plane, okay, and wave reflected from second plane. Wave reflected from second plane. Let me say this is first plane, this is second plane. Suppose the interplanar spacing is d. Let me say like this. Is that okay? Suppose this angle is theta. This angle is suppose theta or phi. I don't know what we take here. Is that okay? So theta. So theta, that's what we take here. Suppose if this angle is theta, so then what is this angle? This angle? It's theta only. So then,
No, sir.
Again, what do we take in case of Bragg law? What do we take? Theta with respect to this one or this one? Quickly.
Sir, I think sir 90 minus theta. Because
This-
it is parallel.
So then if this is theta, yeah, if this is theta, then this should be theta, am I right?
Yes, sir. Yes.
Then look at here, the path, again, the path difference between these two, you have to draw one perpendicular from here to here, you have to draw one perpendicular from here to here, okay? I hope you know this one, we shall deal with this one in crystallography. Now, so this ray traveled this much extra path. So this is d, so that this distance is d sine theta, okay? I mean, sorry, this distance is d sine theta or d cos theta? Wait a second, we write in terms of theta here. Yeah, you have to define theta here only. This is the theta, okay? No, that Gravel sorry, Jetili has taken some other symbol, that's it. Then this should be theta. Am I right? Is that okay, geometry? Or just work it out later, okay? So now these two together, so that is a path difference, okay? So path difference between these two rays, that is nothing but 2d sine theta. So this is d sine theta, okay? So this is also theta, d sine theta, okay? Just work out this geometry, 2d sine theta, okay? When this path difference is integral multiple of, 2 times, what do you call, when this path difference is 2n lambda by 2, isn't it? When that path difference is, what do you call, even multiple of lambda by 2, you have constructive interference, isn't it? We say like that. So that 2 get cancelled, that will be equal to n lambda. This is a condition for what you call diffraction maxima, isn't it? We say like that. Now look at here, this happened for, again, obviously X-ray have got electromagnetic nature, am I right? X-ray is electromagnetic wave, that's why obviously we have no problem here that X-ray has what you call so wave behavior, and it shows interference or it shows diffraction pattern, okay? Yeah, so similar to that one, de-Broglie wave don't require any medium, okay? Wait a second, I'll come to that point. Now look at here, what we do is we do exactly similar experiment, okay? We do exactly similar experiment by taking a crystal of non-interplanar spacing, okay? Let me say like that. Actually in Jetili he has discussed quite different way, I mean historical way, how what you call they did the experiment, okay? But nowadays again we now again we can cut the crystal into one plane actually, okay? So that we can face the exactly one HKL plane. I hope you know that one, HKL, Miller indice and all, isn't it? Again we have some what you call very good arrangement so that are possible now. Let me take again, I am just facing the what you call my incident one, so into a known interplanar spacing. Is that okay? Let me take this one is interplanar spacing, okay? Now in place of X-ray, what I am going to do, I am going to incident electrons. Is that okay? So now look at here, that electrons which are scattered from first one and electrons which are scattered from this second plane, so they are going to now these are beam of electrons, okay? Now these are beam of electrons. Now they are going to what you call interference, they are going to produce the same pattern as that of X-ray.
So beam of electrons?
Yeah, beam of electrons. Is that okay? So beam of electron with known kinetic energy. You know what is kinetic energy is. Let me just mention this one, okay? Whatever he has taken, he know what is kinetic energy is, again because you can accelerate electron via some potential difference, and you can have some known kinetic energy that is equal to 54 electron volt. He knew what is the kinetic energy of this electron beam, okay? I have drawn straight line, but it's the electron beam, just assume like that, okay? So now look at here, he found that, so that's a nickel crystal, so D was known actually, that D is equal to 0.91 nanometer, okay? D is equal to 0.91 nanometer. How do you know that this D? You do X-ray diffraction experiment, you find D. Is that okay? So then do that experiment. That's the best idea. Is that okay? So now again, once you found you have D, you have what you call kinetic energy here. So now look at here. I am going to take this angle as theta. Is that okay? I'm going to take this angle as theta. So then actually in Jatili he has taken this as pi. Should I take the same thing? I hope you can manage with this one. Okay. So now so 2d sine theta is equal to n lambda, isn't it? Again the same equation we are going to apply. So again we are going to observe first order diffraction here. That's why I'll put in case of this 2d sine theta is equal to n lambda, I'm going to put n is equal to 1, okay, for first order diffraction. Okay. So when I put n is equal to, now I'll get 2d sine theta is equal to lambda. Okay. And this is a condition for constructive interference, we say like that, isn't it? And this again this is the angle for which you get maxima, diffraction maximum. Theta is the angle for which you get diffraction maximum, and they found diffraction maximum at theta is equal to 50 degree. That's not this theta that I'm talking about. He's talking about this theta, this angle. For 50 degree, because he will talk about deviation actually. For 50 degree, we got again, if this is 50 degree, what is this one quickly? This is 25 degree. 25 degree, 90 minus 25, what is that one?
Electrons are scattered from there, right?
Yeah, so if this is 50 degree, again he has given this angle, okay? This angle, he has mentioned in a different symbol, okay? Whatever, we need to understand this one, okay? Now, so this is theta, what is theta quickly? 90 minus 25?
25, sir. 25.
90 minus 25, am I right? So that means this theta is equal to, so in that case theta is equal to 75?
Yes.
75? 65 or 75?
15 degree plus 65.
65 degree, okay? So that's equal to 65 degree. So now, or you can write 25 degree, whatever, okay? So now when you substitute, look at here, you know D, you know theta, so you will get lambda from the experiment, okay? From the experiment you will get lambda. Is that okay? So once you get lambda here, again you are going to find lambda from this again look at here, this is diffraction condition, okay? So from this diffraction condition you are going to find lambda by diffraction condition, okay? Let me write like this. So lambda by diffraction condition, you are going to find that one, that's equal to 2 into 0.91, sorry, 0.091 or 0.091. Can you rewrite?
Yeah, 0.091.
D is equal to 0.09. Okay, again whatever the condition that he has taken, we have just taken that one, 0.091 nanometer multiplied with sine of 65 degree. You can write as sine of 90 minus 25. You can write as cos 25. Suppose if you need, whatever, you can find sine 65 degree. Okay, you will get this value. This value you will get 0.165 nanometer. 0.165 nanometer. Lambda by diffraction condition. Okay, we found diffraction maximum at theta is equal to 65 degree. So using all of those values, again we found what you call wavelength of incident wave. Okay. Now what we do is we go for de-Broglie hypothesis. Lambda, which is found from de-Broglie hypothesis, that's equal to h by p. That can be written as h by root of 2m into kinetic energy. I hope you can write that expression. You might have studied this one in class 12, am I right? So kinetic energy is equal to p square by 2m. Then p is equal to root of 2m into kinetic energy, isn't it? So can I write like that? 2m into kinetic energy. Then again he again whatever the incident electron, he knew what is the kinetic energy of that incident electron, and he substitute that one, he is going to find that one, that is 0.167 nanometer. So both are very close to each other. Is that okay? Both are very close to each other. So that means incident electron behaves like a wave of wavelength lambda is equal to h by p. Can I say like this in this experiment? And one thing is, okay, one argument is, look at here, if you want to convince this one to college student, suppose class 12 student, X-ray is a wave, okay, X-ray follows diffraction pattern, so electron follows the similar pattern is same, am I right?
How this angle is 65 degrees?
No, that is measured one. I mean, he found at 50 degree he got diffraction maximum.
Okay.
Maximum intensity of electron or number of electron is more over there. He got in some angle number of electron is more, some angle no electron, like that. Okay, so diffraction pattern. Are you getting my point? That can happen only with a wave, isn't it? Interference and destructive interference, constructive interference, that can happen only with a wave. Student, then the best idea is, look at here, this again, this happens for a wave, am I right? I mean, the X-ray diffraction is X-ray is a wave again, so you get the same pattern as that of X-ray. That's why this should have wave behavior like that, okay? Or if you need very clear-cut idea, again you find this lambda, you again using diffraction maxima and D, so noun D and all, okay? So this is what you call your Bragg condition. So again find the same lambda using de-Broglie hypothesis. So then which confirms that again this lambda, this de-Broglie wavelength is a wavelength of incident wave, isn't it? Or incident wave behaves like so incident electron behaves like a wave of wavelength h by p, that you can see here. So read out Jyotili, he has given that one, but he has taken some other idea. He incident with some other plane, okay, that's it. But we can make it quite comfortable here. I don't think they can design any question here in this concept, okay. Again, so electron can be reflected from this lower layer also, so definitely, so that can happen. Again, you can just work out what is the, I think 2D, 4D sin theta, but you have to read out some so condensed matter physics book, okay. I mean these other layers, this will contribute very less actually. I mean, no, wait a second. I have to check that out, okay. What is the percentage of reflection by each layer? I think he is talking about that one. He has one question. There is some probability the electron is scattered from lower plane can interfere with first layer. Second layer electron with the first layer. No, I mean second, again that's what I have taken. Second layer electron with the first layer.
So that's why the exciting graph is something. I mean the peak is different.
Yes, but for one interplanar spacing you should have only one peak, isn't it?
Yes, we have HKL.
Yeah. So anyway, we shall discuss that one in XRD only, okay?
Yes, sir. We have to make Miller indices for each plan.
Interplanar spacing are same for both.
Yeah. So interplanar spacing is same, okay?
For this line is
So you should say like this. Look at here. These two interfere, these two interfere, these two interfere like that.
yes, sir.
Then again similar condition will happen, okay? Yes. Anyway, we shall discuss this one. But again, this helped us to what you call prove that what you call our matter. I mean that is electron, because you can hit electron and you have it. So it's very well known. Its charge is known. Its mass is known. Isn't it? It's a particle. It has got wave behavior. Okay. So that was proved by Davison-Germer experiment. Now again later, I think or in the same year or something, G.P. Thompson have done similar experiment. So again incident electron which falls on thin film, and he's going to get diffraction rings, okay. I hope you have studied that one in class 12, isn't it? It was there in class 12. Yes. Now look at here, one thing is proved here. Yeah, any question here quickly? Any question?
How that de-Broglie wavelength has derived lambda equals to x by c.
Okay. E equal to mc square. E is equal to mc square. E is equal to h nu, isn't it? These two are clubbed. I think it was there in class 12th, this derivation. So can anyone guide me quickly? If I take m into c as the momentum of the order of momentum, m into c, h nu by c into c. Is that okay?
I think
The neighbor
like half only
Half
only
half mh square. No. Not kinetic energy. No. E equal to mc square. That is again somehow what with that one actually. Because by the time you had a special theory of relativity also, isn't it? Momentum.
Sir,
Yes.
so we can write nu equal to c by lambda.
No. Let me write this one as P into C equal to P into C. Okay. I better to write like. Look at here. I better not write mc square. I go for what you call photon. For photon, energy is equal to P into C. Energy is equal to h nu. So then P is equal to h nu by C. Again, I better to share the original paper by de-Broglie because it's 1 or 2 page, I think. Okay. So P should be equal to h nu by C. P is equal to h by lambda. I think he might have what you call. No. How he got the idea that material particle have got that nature, isn't it? It was there in class 12th. Anybody? Yeah. Anyway, we shall. I'll share the original paper by de-Broglie. Okay, because it's I heard that it's only 1 page derivation, and we will get his words, isn't it? What exactly he has done and all. Or if anyone finds that one, you can quickly share before me. Okay. I think this kind of idea. Okay, E is equal to P into C, E is equal to h nu. Those are clubbed so that again you can relate the P to wavelength. Okay, like that.
Sir, one question.
Yes. So tell me.
Sir, graph which we obtained from de-Broglie experiment, sir, can you draw?
I think in experiment they do with some other plane. Okay. I don't feel that is comfortable right now because we know again what is the plane, what is the angle like that. They are going to make this kind of thing. Okay. Again, this is I have done so that it is very comfortable to see path difference and all. Okay. The exact thing that they have done is exactly below. They have taken it like this.
No, sir, some graph obtained.
Wait. First, let me take this one. So they take some other plane, but nowadays we can find all interplanar spacing actually. Okay. So I think they might have taken this kind of plane. Is that okay? They might have taken this kind of interplanes. So they take what you call a ray which is scattered like this. Okay, and you have to do again draw normal so that this angle is known. Okay, this angle is some 50 something degrees, isn't it? So that's what known. Okay. But again, this is the crystal. Okay, this whole thing is a crystal. That's how they have taken. Okay, that's the only small difference. So this D again actually they might have known this D, then somehow they will find this D also using some geometry and all. Okay. Now again in this kind of experiment, look at here. This is theta. Okay. Remember earlier I have taken some other angle as theta. Be careful. This is theta. Okay. They draw theta is equal to 0 degree to theta is equal to 90 degree, they get maximum. At 0, they get some maximum. At 50 degree also they get maximum. Look at here. He has drawn it like this. So theta 0, okay. So theta is equal to 0. So theta is equal to 90 degree. If you for 50 degree, so theta is equal to 50 degree, you get a kind of maximum. And for 0 degree also he has drawn one maximum actually. I mean it might have passed through that one, but what you call its height is low. Is that okay? Its height is low like that. Now again, you should see the arrangement of this what you call it. So they will have some arc kind of shaped, so a detector which is movable around the arc actually, so that you can go for different thetas actually. Okay, they have that kind of arrangement, so that they found at 50 degree, again at 50 degree they found diffraction maximum or more electrons. Suppose for some other angle, no electron for some angle, no electron at all for some angle, maximum electron for some other angle. Are you getting my point? That says kind of constructive destructive interference, isn't it? So can you keep checking YouTube? You have mobile? Again he's saying de-Broglie didn't give any explanation. He thought if it is true for proton, it should be true for particle. I think the same idea that I gave. Okay, yeah. That might be true, isn't it? E is equal to P into C. E is equal to H nu. Okay, E is equal to H nu. So then you can define H nu by C into C here, so that P is equal to H by lambda, 1 by C by nu, that is equal to lambda. If that relation is true for photon, which believes to be a particle, it should be true for all material particles. I think that again this equation is what you call invert, again solved for lambda, H by P. Okay, might be. Okay, we better to share, okay, because since it is very small paper, I think we can read out whatever de-Broglie said in the initial. Any what doubt you had here in this one?
Sir, I want to ask that one value corresponds to two values, sir. How that is possible?
No, one value. I'm not getting. No. We are not drawing intensity here. We are saying this is maximum intensity like that. With respect to intensity, you should draw like that. Intensity versus theta. Okay. So at 50 degree, you get maximum. Just see X-ray diffraction pattern. It's not drawn versus intensity versus theta. It is theta for different angle he wanted to show actually in that graph. Okay. Anyway, I don't think they designed any question out of it. Anyway, I'll search old question paper. If I get any question, then we shall get into what exactly they have done. I don't think we don't need what exactly they have done. Okay. You need to understand that again in one direction, no electron. In one direction, maximum electron, that can happen only kind of superposition happens. Am I right? So that is the main part here. Is that okay? Quickly. Yes. Any question? Now I'll give some ideas. Then I'll share a notes. You read the notes. Okay. Then I'll come online again. Again, de-Broglie hypothesis says. De-Broglie hypothesis says again all material particles have got wave behavior. Am I right? Whose lambda is equal to H by P. Now again, if you ask what kind of wave it is, we don't know, isn't it? And again, it's not a mechanical wave, it's not an electromagnetic wave, it's not the kind of sound wave. That's why we call it as matter wave, since we don't know. Is that okay? And one more thing is this MVR is equal to NH by 2 pi, not MVR is equal to NH by 2 pi. I'll go to what you call Bohr-Sommerfeld quantization. I hope that's equal to P dq. Am I right? P dq is equal to nh. And again, so the same can explain what you call so E is equal to nh nu in case of so linear harmonic oscillator. Our Planck's idea. Okay, the same equation can explain that one also. Okay, so now look at here. One more thing is so this also helps us to prove many quantization rules actually, Bohr-Sommerfeld quantization. Or let me take before that one you have MER is equal to nh by 2 pi, and later you got again wave behavior of what you call material particle, lambda is equal to h by p. Remember, again this gave some idea. This gave some quantization. Okay, so this gives some idea that yeah, material particle behaves like a wave. It undergoes interference and diffraction. But these are not a framework of the theory. Is that okay? So these are not governing rule. We need more fundamental governing rule here, just like Newton's second law, where you can apply Newton's second law anywhere, isn't it? We need more governing rule. These are not governing rule, remember. So again, this is a hypothesis. This is a kind of postulate, isn't it? So this is a kind of postulate. Now you can't apply those things for any situation. You may find only energy eigenvalue, isn't it? So you will not get any other information here. Superposition of state, that kind of more information that quantum mechanics might, again, our microscopic things might be playing. Yes.
Sir, after proving the hypothesis from the de-Broglie experiment, so is it like hypothesis again or something different?
No, that is true. That is true. It has a wave behavior.
Yes.
Again, it will undergo interference and diffraction.
So is this a hypothesis?
But what is that wave behavior? That we don't have much understanding. What is that wave behavior? What is that wave? Isn't it?
Nature of the wave.
Yeah. So I think after de-Broglie hypothesis only, Schrodinger got some more idea. That's why they called that psi as wave function. Wave. The word wave came. Even though its use is different. Its use is to do some probabilistic interpretation. So, but they call that as wave function, isn't it? Again, so they might have dragged what you call this de-Broglie idea, so to find some equation, more general equation, which explains all consequences of wave behavior. Okay, this lambda can explain only one consequence of wave behavior. What is that? Interference and diffraction, superposition, isn't it? But again, we need a generalized equation which holds all consequences of wave behavior, just like what you call interference and diffraction also, and discreteness of energy also, superposition also, like that. We need more general theory here. So while developing that more general theory, we don't give more importance for wave picture or particle picture. Okay, while developing new theory, while developing new formalism, who cares, isn't it? Whether it is a wave or particle, isn't it? Again, we need a kind of governing rule, isn't it? We need to understand what is the law of nature. We need to understand what is the rule of game that nature is playing. Are you getting my point? We need to understand, or we need to observe, and we need to catch what is the rule of the game. Look at here. Suppose I think this also said by Feynman only. Suppose suppose you don't know how to play chess. Okay, suppose you don't know, but so couple of guys are playing the chess. You are watching that one for a long time. You can understand the rules of the game, isn't it? So like that, again, we need to find the rule. Again, now we are not understanding what nature is playing, isn't it? So these things are confusing us. Electron, which was particle for us, isn't it? Now again, look at here, it's a wave. What kind of wave, we don't know. Again, we believe that light is a electromagnetic wave, isn't it? Now look at here, it's a photon, isn't it? It is quite confusing us. We don't know, we are not grabbing what is the rule of the game that is played by the nature. And our next attempt is to understand that one. After understanding, we can make a framework. We can write a game book, rule book, isn't it? That is quantum mechanics, isn't it? And why that is important? Well, again, look at here. This also gave old quantum mechanics. We call this as old quantum mechanics. This also gave quantization rule, isn't it? Why it is important? But once you have what you call framework, so that can predict new phenomena. That framework is done using the what you call earlier experimental facts, this hypothesis and all. Okay, but that framework that can explain the phenomenon which are not explained. Not only that one, our idea is to develop the framework which can predict new phenomena. That's why we need to understand that one. That's why we are not happy with these things. So that is the next attempt. That is a double slit experiment, which is very, very important, because I'm going to code that double slit experiment throughout quantum mechanics. Whenever superposition state comes, I'm going to code that one. Okay, double slit experiment and uncertainty principle. These two are very, very important. Okay, and